Okay, so lastly, when we talk about angular and rotational motion, we need to talk about angular momentum. So linear momentum, we can define angular momentum as moment of inertia times angular velocity. We can then write the total torque as being the rate of change of angular momentum. So if the net torque is zero, the angular momentum is constant. Okay? If net torque is zero, angular momentum is constant. Therefore, systems that can change their rotational inertia through internal forces will also change their rate of rotation. All right, and this is something you can see if you have an ice skater that's skating and starts to spin, but then as they bring their hands closer together, as they take their eye and make it smaller, their angular velocity increases, which makes them spin faster. So as they get closer together, as they change, right, as they change their eye, as it gets smaller, angular velocity increases if momentum stays constant, which it should, right? Angular momentum or momentum is always conserved. So here we go. We got the diver. The diver straight up, not moving very fast, but as the diver tucks, makes the eye get smaller, which increases the angular velocity, which makes the spin faster. And then once the diver reaches the spot where the diver does not want to spin anymore, it increases the eye, which makes the spin less, so they can hit the water at the angle they want to get the least amount of splash. But the point is that if momentum is conserved, which it is, right, that if we change I, which is our distance, and make it smaller, things will spin faster. So let's use our hand, and I can't really demonstrate this. I might try to demonstrate it as we discuss problems. But the angular velocity vector always points along the axis of rotation. Its direction is found using the right-hand rule. So what I mean by that is you have something spinning, okay? The fingers go in the direction of which you're spinning. And then whichever way your thumb points, okay, is the direction that velocity vector goes. So spinning this way, velocity vector goes up. If it was spinning the other way, velocity vector would go down. Okay, that's called, and use your right hand. It's called the right hand rule, and I'll demonstrate that hopefully with some of the practice problems. Angular acceleration and angular momentum vectors also point along the axis of rotation. So here we go. This is the way we're going here. And you can see the momentum of the person up, momentum of the platform down. And that's how we can find the axis, and that's how we can find that, okay? Again, discussions we'll talk about as we see individual problems. So here's a long example. I'm going to read through it, and hopefully it can make sense as we do it. So a clutch, like on a car, or any kind of motorized vehicle, consists of two cylindrical plates that can be pressed together to connect two sections of an axle as needed. The two plates have masses ma that's 6 and mb that's 9 kilograms with the same radius of 0.6. They are initially separated, as you can see in the diagram. Plate ma is accelerated from rest to a velocity of 7.2 radians per second in 2 seconds. We want to find the angular momentum of ma, b, the torque required to accelerate ma from rest to 7.2, and then next, plate B, initially at rest but free to rotate without friction, is placed in firm contact with freely rotating plate A. And the two plates then both rotate at a constant angular velocity, which would be, we will call W2, which will be less than W1, right? Because that's momentum. Why does this happen, and what is W2? Do it now.
All right. So we got our two parts of our clutch. A is moving in this direction, starting with this initial velocity, finishing with this velocity over this amount of time. Has a mass of 6 kilograms. The second part of the clutch is 9 kilograms. They both have the same radii of 0.6 meters. So part A, and I'll repeat it, asks the angular momentum of MA. Angular momentum is equal to the moment of inertia of A times the angular velocity. Now it's a cylinder, so the angular moment, the moment of inertia of a cylinder is equal to 1/2 ma r squared. So I substitute this in for I, so LA is equal to 1/2 ma r squared WA. Now I can substitute because I know all this. So I get 1/2, my mass is 6 kilograms, my radius is 0.6 meters squared times how fast I'm going, which is 7.2 radians per second. And I calculate all this up, and I get 7.8. Now our units for angular momentum are close to what they were with regular momentum, but it's kg m squared over s. So those are our units for angular momentum. All right, so I have this. So I have angular momentum. So part B asks, again, I'll read it. The torque required to accelerate ma from rest. Torque, change in momentum over change in time. We start from rest, so our momentum initially is 0, and our final momentum is this. So final momentum is 7.8 minus 0 over our time of 2 seconds. So essentially, our torque is going to be 7.8 divided by 2, which is 3.9, and units of torque are meters times newtons. So we have torque in our clutch of 3.9. And then we move on to C, and C asks, next, plate MB initially at rest but free to rotate without friction is placed in firm contact with freely rotating plate MA, and the two plates both rotate at the same angular velocity, which is less than the initial. Why does this happen, and what is it? Okay, well, first off, moment of inertia of A times the initial velocity is what we're looking at here, right? So we know that that whatever A is spinning when they touch, which essentially is going to be this, right? So I could call W final, but it's initial for the system. That's going to be 7.2, and then this is going to be whatever I of A is. And then after they come in contact, just like we did with linear momentum, the masses come together, it's going to add together. So we add their moment of inertias together times, and that will get us the final. So essentially what's going to happen mathematically is this. It's going to be less than this, right? Or at least we hope it to be, okay? So as we look at this, we know I of the cylinder is 1/2 ma r squared, okay? So I go 1/2 ma r squared wi equals, and then this is going to be 1/2 ma r squared, whatever this, right, plus 1/2 mb r squared. The camera's not getting there. 1/2 mb r squared for what we're solving for. Now, ideally we would just substitute in, but I'm going to show you something mathematically that might make your job a little bit easier. Since r squared is all over the place here, I can get rid of r squared. I can also get rid of the 1/2. What that leads me to is this. ma wi is equal to ma plus mb wf. Just makes things a little bit easier mathematically. Now you could solve it, but you'd find all those things would end up canceling out in the long run anyway, so it really didn't help you. So if I have the mass of A is 6, and I know it's traveling 7.2 radians per second, A plus B masses, 6 plus 9, 15, would be final. So I divide both sides by 15, and I can solve. This one I didn't write down, so I'm going to calculate with my calculator here. But what I see is 6 2 divided by 15, 2.88 radians per second. So we're going from 7.2 to 2.88. And that's just conservation of momentum.
And then we're going to talk about neutron stars. Astronomers detect stars that are rotating very quickly, and they're known as neutron stars. A neutron star is believed to form from the inner core of a larger star that collapsed under its own gravitation to a star of very small radius with very high density. So all the mass in the star goes to a lot smaller area. Before collapse, suppose the core of such a star is the size of our sun, which approximate radius 7 times 10 to the 5th kilometers, with mass 2 times greater as the sun, and is rotating at a frequency of 1 revolution every 100 days. If it were to undergo gravitational collapse to a neutron star of radius 10 kilometers, so look at how a radius is going from here to here, what would its rotation frequency be? So the frequency is 1 every 100 days. What would it be now? Assume the star is a uniform sphere at all times and loses no mass. Do it now.
All right, neutron star. So this is a definite, this is going to be conservation of angular momentum, where initial momentum equals final momentum. We're going to assume that masses are the same for both of our star, neutron star, and then where the star came from. So we're going to do a little bit of algebra here, and we're going to solve this in terms of W2. So we're going to say that if we want to solve this in terms of W2, that W2 is equal to I2 W1 over I2. Now, if we're talking about a star, which is a sphere, it should be 2/5 mr squared. So that's going to be 2/5 mr squared over 2/5 mr squared times W2. Now we assume the masses are the same, and this is the same. So really, the only thing that's going to be different are going to be what the radii are before and after. So W2, it should be W1, sorry, W2, so the final angular velocity is equal to the radius squared that we start with, so radius 1 squared over radius 2 squared times the velocity of 1. All right, so this is how we could find. So if we knew the radii and velocity, we could get there. And then it says, so we're there, and then it says, if it were to undergo gravitational collapse to a neutron star of radius 10 kilometers, what would be its rotation frequency? So the radius of the sun is 7 times 10 to the 5th, so that's going to be R1. So W2 is equal to R1, which is R1, 7 times 10 to the 5th. And then R2 is going to be 10, and both of these are going to be squared. And then what's the velocity of the sun? And if it it says the rotated 1 revolution every 100 days. So if we want to do radians per second, right? 1. Get where I can show this to you. 1 revolution every 100 days. And that should be what the sun is doing, right? Yeah. Oh wait, no. One revolution every 200 days would be the final velocity, okay? So that would be W2. So we're going to take a different path to solve this now. If we're looking at frequency is going to be W2 over 2 pi. frequency, and that's going to equal, just changing this up a little bit, R1 squared over R2 squared times frequency of 1. And this will make things a little bit easier, I think, but we'll see. So we know that R2 over R1, like we said previously, is 7 times 10 to the 5th and over 10, both squared. Our frequency is 1 revolution every 100 days for our star. So 1 revolution every 100 days should be 1 rev, 100 days. We want to get this into revolutions per second. So if we go 1 day is equal to 24 hours, and 1 hour is 3,600 seconds. We got revolutions per second here. Okay, so now we can solve all of this to find our frequency 2. So calculator, and I apologize, I thought I could do it one way, but this way looked like it would be easier. So 7 exponent 5 squared divided by 100 gives me a big number. And then I'm going to multiply this by 1. And then I'm going to divide it by 100, divide it by 24, and divide it by 3,600. And I get 567 revolutions per second. Okay, and then if we want to find what that is, it's about 600 hertz, right, per second. We just flip it, take that, and that's about 600 hertz, right, per second. And if we want to find it revolutions per minute, even though I don't think it matters, we just multiply by 60, and that would tell us how many revolutions per minute. But this was how you get revolutions per second. So we made angular momentum the same, knowing the masses were the same. We were able to come up with this equation, which was beneficial as we wanted to solve for frequency. And again, I tried to do it a different way, but this way looked a lot easier.
Another example, spinning bicycle wheel, something maybe we could try to demonstrate in class. Your physics teacher's holding a spinning bicycle wheel while he stands in a stationary frictionless turntable. Be nice to have one of those, right? What will happen if the teacher suddenly flips the bicycle wheel over so that it is spinning in the opposite direction? Do it now.
All right, so the bicycle tire, this is my drawing. So we have the teacher standing on a rotating object that's stationary, has a spinning bike tire that's spinning this way. We know momentum is going upward because of the right-hand rule, right? We take our right hand and we show the direction. So if it's spinning this way, right, I'm going to put my hands in the same direction of the circle, which means it's up. If it was spinning the other way, my momentum would be going down. So my momentum's going upward, okay, because of the right-hand rule. It's spinning towards or out towards you, which means the thumb goes up, and that's what the direction of the momentum. So that's why momentum's going up. If we take this and turn it upside down, all right, what happens is now our positive L, as it goes down, becomes negative L, okay? Now the bike tire will start to spin and we can see as we go down, right, it's going to change directions. This is, but what's important to understand is this change in momentum, all right? So here's initial, here's final, okay? Initial and final. So now we take a look at our change in momentum. Is that we think about the change in momentum for the teacher, right? Change in momentum for the teacher will go from L minus negative L, which is L plus L, which is 2L. So the momentum of this will be 2L, and it'll be going in the positive direction, so it will spin this way. Difficult to try to prove. Maybe in class we'll get the bike tire out and try to do it with the spinning chairs. It's hard, just because of the spinning chairs don't spin perfectly. This is a lot better way to show it, but I think we can try it and see. If we can get a light enough person on the chair, maybe we can get it to work. But that's the reason behind it.